Okay guys, before I started today's actual video, I wanted to clarify a couple of questions that a few of you had regarding the difference between the definite integral and indefinite integral. So here's a chart that compares the main differences. There are tons of them, but I think for the purposes of our course, as of right now, these are going to be the most important differences. First of all, the definite integral is used to calculate the area under a given curve. So we've seen that. I don't need to draw any pictures. Uh, by doing so, the area is going to be an actual number. It's going to be a number using square units. And this is no secret for anybody. When we get the indefinite integral, it's and here's the thing. We get a function, and we add plus c because we need to take a constant into account. And a few of you realize this because let's say that I get my function f of x is x plus 2. If I take the derivative, f prime is going to be 1, and if these were x plus 6, the derivative is also going to be 1. So when I get the antiderivative, I know that the antiderivative of 1 is x, but I have to take into account this constant that turns into 0. It could be anything. Because it could be anything, the answer is not definite. It's not an exact answer. It could be so many things. We call it indefinite integral. That's the simplest way to explain it. A definite integral, we don't take the constant into account, and we get an actual number. So let's see, you also have boundaries to calculate the area. Here you don't have boundaries. The result is a number, the result is a function. The process, however, is the same. There's an extra step to calculate the definite integral, but the process is exactly the same. Okay, so if you have any questions on this, please shoot me a message. We're going to get into the actual chunk of today's lesson, or I should say tomorrow's, and it's U-substitution. U-substitution is an integration technique. Just like we had a ton of differentiation techniques, we have a few integration techniques that we're going to be using. This one, it's quite handy and quite easy to use once you get the hang of it. And all it's going to do is, you're actually going to do this, just substitute. Notice that we have two different functions here. We have a function x and a function x minus 2 to the fifth. And what U-substitution requires is that you take the most complex one out of these two. In this case, is x minus 2 is a little bit more quote-unquote complex than x, right? So we have x minus 2 has a minus 2, and x is just by itself. So we're going to let u be x minus 2. And the whole idea of this is to rewrite this expression into something that it's easier to deal with. So let's go ahead and see what happens when we take the derivative of this. So we could substitute now x minus 2. I could put a u instead of x minus 2. Let's see what happens once I take the derivative of this. If I take the derivative of u, I would get du, and my derivative, the derivative of x is just dx. Derivative of negative 2 is just 0. What else would I need? So I know what I could substitute x minus 2 with, so I guess it's best if I show you. I can replace this x minus 2 using the u. I can just go ahead and say u to the fifth dx, we agreed, is the same as du. But now I still have an x here, and I don't want an x because I'm integrating in terms of u now. My width is going to be in terms of u, and I don't want x. So how could I come up with the equivalent of this? And the answer is actually going to come from here. I could go ahead and say that this is the same as x is equal to u plus 2. And now I'm going to have something like this. I'm going to have u to the 5th du. And now I'm going to have u plus 2 here. So what would this end up looking like? It's very simple. I'm going to distribute this. I'm going to rewrite this so that it's easier to see. We have u to the 5th times u plus 2 du, but this itself is u to the 6th plus 2u to the 5th. And at this point I'm ready to integrate. So I'm going to do just that. Oh, I forgot the most important part, the du. Sorry about that, guys. So I'm going to integrate this u to the 6th plus 2u to the 5th du. And this is now easy to do because I can just say, I can just do my power rule backwards, which is u to the 7th over 7. I'm going to have 2u to the 6th over 6th over 6th, no, over 6. So I'm going to have u to the 7th over 7 plus u to the 6th over 3. And remember, since this is an indefinite integral, I have no boundaries. I'm going to do plus c. Now I'm ready to throw back the actual value of u, which is x minus 2. So I can say that capital F is x minus 2 to the 7th over 7 plus x minus 2 to the 6th over 3, and I cannot forget my plus c. Okay, and I promise you guys, if you were to take the derivative of this, you would get just that. Any questions, please shoot me a message. Here's a more complex example. Let's say that I ask you to integrate, we want to integrate 2x times the square root of 3x squared minus 1 dx. And we're going to use U-substitution. And the question is, what do you use to be u? What function do you choose to be u? And again, I'm going to ignore the radical for a minute, and I'm going to ask you to compare 2x to 3x squared minus 1. I told you to choose the most complex out of the two functions, which is going to be, in this case, when you compare 2x versus 3x squared minus 1, well, we know that this is the winner as far as complexity goes. So I'm going to erase this for the sake of space. So I'm going to let u be 3x squared minus 1. And to find dx, I'm going to go ahead and integrate du, because I'm integrating this in terms of x, so my derivative is going to be 6x dx. Because again, I'm integrating in terms of x. Sorry, I'm differentiating in terms of x. I'm taking the derivative in terms of x. So what do we have here? We have the 3x minus 1, check. Dx, not quite, because technically speaking here, I can go ahead and separate these as 3x squared minus 1 times 2x times dx. And I almost have that, but not quite. So I can go ahead and rewrite this as 2 times 3 times dx. And I can go ahead and divide by 3. If I do that, I get a 2. I know that 2. Sorry, this was 2x. I know that 2x dx is equal to du over 3. Now, I'm ready to substitute. So what can I do now? I'm going to take this guy over here, and I'm going to write it again just to make it easier to substitute. So now, 3x squared minus 1, I know that I can just substitute like this. Now, I'm going to go ahead and put the 2x dx together. What is 2x dx? It's 1, well, I'm going to do du over 3. I was going to do 1/3 du, but it makes no difference. Times square root of u. This looks kind of weird, so I'm going to rewrite it as square root of u over 3 du. So now I'm ready to start differentiating. I keep using that incorrectly. I'm ready to start integrating. I need to start getting used to saying integrating. We're getting ready to start taking the integral. So what can I do? I'm going to go ahead and rewrite this expression as u to the 1/2 divided by 3 du. So I'm going to go ahead and use that rule now. I'm going to add 1 to the exponent. So I'm going to add 1, and I'm going to have u to the 3/2 divided by 3. And now I'm going to divide this whole thing by 3 over 2. So again, when I do this, remember that I'm going to use this little technique. And I'm going to get 2 u to the 3/2 divided by 9. So now I'm ready to go ahead and substitute. Oh, and I forgot my plus c. That's a very important thing. So now I know that a capital F of x equals, and what's u? U was 3x squared minus 1, or 2 times that, to the 3/2 divided by 9 plus c. All I did was substitute u back into my result. And this is my answer, guys. Please copy these 2 examples and be ready for practice tomorrow.